All right, hello again. So to finish off talking about statistical significance tests, I'm going to give a modified version of a presentation I gave that accompanies the paper that has been put into Learn. I still need to tell you what those parts are of the paper to read, but it is primarily the introductory material. This will give you some other examples of statistical testing for in information retrieval. That's the primary purpose of this. I'll also talk about some other things. All right, so here we go. And actually, this shows you how dated this is, that it's not in widescreen format. And I'm sorry, I didn't change my screen capture device to be in old standard format. Anyway, so we've talked a lot in the course so far about how we do ad hoc retrieval evaluation. Often we've got something like 50 topics. We take a pair of systems. We run those systems over the topics. We compute our metric, and then we summarize it with some sort of statistic, some sort of summary statistic. We want to evaluate these two systems, but there is inherent noise. Now, it's not noise like when we were talking about two runners on the track and, pebbles and wind and heat and things like that. The variation here is coming all from the different choices of the topics. Okay, so we only have a sample of all of the possible search topics. And so the variation here is with the number of topics. We want to know whether or not we truly have a statistically significant result. And we want to be sure to only report significance when it truly exists. We don't want a false positive. We don't want to falsely report things to be significant when they are not actually significant. So how do we do this with our tests? Well, again, just to give you an example, you could probably see this in papers and places. You have two systems. They report their mean average precision over these 50 topics. And wow, system A is a relative 25% improvement over system B. But you'll see the big thing is in the caption, something often comment about whether the difference is statistically significant. And here they say it is statistically significant. And then actually this is full 5 points in the mean average precision, going from basically 0.20 to 0.25, or even, it's basically 5 points. If we were to think of that as percents, 5 full percents, but relative improvement is 25%. And this is, I'm quite certain that this is actually statistically significant. And we're going to actually use these two systems to do a comparison with them. All right. And so what do we actually see here? What is a statistical significance test? Well, as I mentioned in the lecture, we always need this test statistic. This is the measure that we're doing to compare the two systems, applying to those differences on for each pair of measurements. So we measure each system on each topic. We can take the difference. Now, what's the summary statistic that we're going to use? That's our test statistic. Mean is very common. You could also do the median and some other things. We then need to actually compute this distribution of this test statistic given the null hypothesis. A common null hypothesis is there's no difference in the systems. This is us saying the systems are the same. So what is the distribution of this statistic for these two systems under this experiment if there was no difference? So this imaginary world where they're identical systems, obviously they're not. They're computer code, and we made changes to them. They're not the same system. But if we were to imagine them to be so, what would this distribution end up looking like? And then we're going to produce a significance level. This is talking about the p-value or the probability that we would see a result of this large or larger for the difference of those systems. So here we go. We got these two systems that we started with in our introduction, System A and System B. And these are real information retrieval runs that were once upon a time submitted to a track and 50 topics, get the individual average precisions. And then we average them to produce a mean average precision. And I didn't mention this earlier in the course, but saying average precision is a little weird. And so people say mean average precision, and they abbreviate it MAP or MAP. So what's the difference between those? Well, it's 0.052. So we need to compute this distribution of a test statistic under the null hypothesis. And so it could very well look something like this. Once we've computed it, then we go and we look at the amount of the distribution, which goes for a difference that's greater than that 0.05, I believe it was 0.052, yep. So we look at that which is greater than that, and also that which is less than the negative 0.52. And again, remember, we do these two-sided significant tests because before we run the experiment, we do not know whether we're going to produce a improvement or produce actually it could produce a system that's worse. We hope it's going to be better, but we don't know. And so these could have gone in either direction. Again, under the null hypothesis, we could have subtracted one system from the other system and we wouldn't have known which direction. And so we need to consider both sides of the distribution, both tails. And we take the shaded area to be the p-value or the significance level. And again, in a typical distribution here, the area under the curve is 1. And so it is just the shaded area then that is the p-value. All right. We're going to look at 5 significant tests in this presentation. The student's paired t-test. So again, we are considering always the circumstance when we have pairs of results. So we have a measurement of System A and System B both on the same search topic. Also the Wilcoxon signed rank test, the sign test. We'll also look at the Bootstrap and Fisher's randomization test, also often known as the permutation test. So let's look at these in turn. A randomization test, its null is that the systems A and B are identical. We could pick anything for our test statistic. In this example, we'll use the mean difference. How do we produce this distribution under the null hypothesis that A and B are the same? Well, we do this for each topic. We randomly exchange A and B's scores. That's the same thing as when in the other presentation I said we flip a coin and change the sign. Then once we've got that randomized across the 50 topics, then we record our test statistics. So for example, the mean difference again. And we repeat this over and over. There are a total of 2 to the 50 permutations, so we're not going to do that. That's too many. So what we do instead in these experiments here is we do 100,000 random permutations and record what the test statistic is under the null hypothesis. So here's our example. We have System A and System B. Each one of these rectangles represents a topic, and there's some score. Imagine actually that it went on for all 50 topics. So when we measure the we average the differences, and it shouldn't actually be the map difference. It should be, well, it could be the mean average difference in the mean average precisions, because the difference at the per topic level, which is the average precision, the average of all those differences is the same as taking the two averages, the mean average precision, and taking their difference. So anyway, we go and we randomly shuffle them, and we record again the value of our test statistic. And this time it's only 0.021. And then we continue this process and we get more and more measures as it continues on. We keep doing this repeatedly, and each one of these is a possible experimental outcome over the for the null hypothesis for this experiment. Again, under the assumption that A and B are identical systems, and the only difference was we chose to label one to A and one of them B. We could have actually had either one be the result. It was just some randomness that caused this difference. And then so we can simulate this. We do that 100,000 times, and we get this nice distribution under the null hypothesis for the randomization test. We can then count these tails for the number of values, which were greater than the actual experiment of 0.052. And here we actually get a p-value, a significance level of 0.0138. So this seems to be a pretty unlikely thing that this difference between the runs is just a random fluke. It's just from the set of topics. It seems to be that it actually is probably a very real result of the experiment. Wilcoxon signed rank test. I'm not going to go over this in detail, but I think one thing I want to point out, first of all, is it has its very own test statistic. It does this rank score differences it ranks the score differences by absolute value and so forth and so on. Its test statistic is not the mean average, is not the average. Okay, so already it's a different type of test, and it was actually generated, it was designed in 1945 to be something that you could actually do by hand quite efficiently, and look things up in tables and so forth and so on. With the advent of computers, this doesn't make any sense, and it doesn't make any sense at all because it is the same as the randomization test. It just has a different test statistic. Given that we can run the randomization test with any test statistic, and we can run it really quickly with today's modern computers, there doesn't even seem to be a reason to ever use the Wilcoxon signed rank test. You're just choosing a different test statistic, which you won't be usually ever reporting. You don't, systems A and B are different by this test statistic. That seems for the Wilcoxon signed rank test doesn't seem to be ever what any people are doing. They're applying the test, and the actual statistic that they're reporting is different, which is a bit of an issue. The sign test is when we want to talk about the number of wins versus the number of losses. There's a version that you can also say, I'm not going to call it a win unless it's actually greater than a certain amount. Here we show an example with where we require the difference to be at least 0.01. Then we we're able there could be ties, and so then we reduce the number of trials, so to speak. Anyways, it turns out that the sign test as well is the randomization test. It's just, again, with a different test statistic. This time the test statistic is how many of these topics was this system better than that other system. All right. You have a Bootstrap test. It's slightly different null hypothesis. Now, again, though, like the randomization test, you can choose anything to be its test statistic. It proceeds in a fashion that's a little bit similar to the randomization test, but different. All right. And so, by the way, each time I've been doing these slides, I've been reporting these p-values. So we started with a p-value of basically 0.06. Then it went all the way up to 0.36. So 36% of the time we would have expected these results under the sign test. Wilcoxon signed rank test is 0.056. And the randomization test was lower, the 0.0138. Bootstrap, won't get into the details of how it's done, but you can use any test statistic with it, and that's really great. Its p-value is in line with what we saw for that randomization test. And then finally, the student's paired t-test. There's often been concern in information retrieval. You'll see this in some of the early textbooks about, is it okay to use students paired t-test with its assumptions that there are, you require these normal distributions. All the evidence has pointed out that, especially as the number of samples gets large, the students t-test is certainly very applicable and robust to violations of any assumptions about normality. When we do 50 topics, we're well past concern of these violations of normality. And we see here again, it's actually got a p-value of 0.0153 in line with the randomization test and the Bootstrap. Interesting to note that it was created by a statistician for Guinness, the beer brewer, I guess, in Ireland back in 1908, published under a pseudonym as Student. So it really should be Gossett's paired t-test, but it's been called Student for so long that I don't think that's ever going to happen. Brewers care a lot about statistics. There's a lot of variability in crops, and they're always trying to understand how to actually measure and do things in a statistical fashion so that they can get beer that always tastes the same. All right, so this is the summary of those p-values for those different tests. At least in this one example, the randomization, the Bootstrap and Students T are well in line with themselves, but the Wilcoxon and the sign are saying, well, if we set our significance level at 0.05, then nope, we don't have a significant result here, whereas the randomization sign, Bootstrap and Students T, all do say there is one. Of note, again, that the randomization, Bootstrap, and Students T, we're able to all use here the same test statistic, which is the mean difference. We can get randomization and Bootstrap to use any test statistic that we want. Whereas in here, the Wilcoxon and the sign, they're not using the test statistic that we're reporting here, which is the mean difference. And so this is what's going to lead to problems with their usage. So again, which one should you use if you're an information retrieval researcher? So the idea of this work really was to say, it doesn't matter what test you use if all the tests give the same results. If you would be making all the same decisions always with these tests, then you could use whichever you wanted to. But if there's some differences in opinions, then we should try to understand that and what's going on. So we ran an experiment where we took a whole bunch of runs, measured their performance, compared them pairwise to each other, and then produced the various statistics that we needed. This is what happens when we see the randomization t-test in Bootstrap with a bunch of p-values being produced by this experiment. And we can see here that they largely agree with each other. So if we had to, talk about, well, is this test better than that test, and so forth and so on, given how much agreement there is here, it doesn't seem worth arguing about anything. Use the one you want to. You're going to end up making the same decisions. On homework 3, the idea will be to use the student's t-test, of course, paired, two-sided, and that's because it's in every piece of software, including Excel, that you would want to use, and the options are there to use it correctly. You could even take a close-up and you could see that they're largely in agreement with each other. What happens when we look at the randomization and the sign test, which have these different test statistics than the other statistical tests? Here we compare it to the randomization test, which the plots would look very similar for the student's t-test and as well for the other one. So, but these guys there's huge differences in the p-values they produce. And again, why is that? It's because they actually have a different test statistic. All right, so you can make all sorts of mistakes with using them if you're reporting the mean difference. You're going to miss cases where you have actually discovered something works better, And likewise, you're going to potentially make mistakes declaring things work when they don't. So yeah, definitely problematic. I will say that again, if you want to report the number of wins or successes or whatever, the sign test is great. Absolutely. Again, it is the randomization test. It's just with a different test statistic. All right. So there really is no difference when we want to report, for example, the mean, average, precision. We want to put the mean of anything. There's no practical difference, at least for the experiments run here, between what we saw with the randomization, bootstrap, and t-tests. When you're reporting the mean difference, absolutely don't use the Wilcoxon or sign test. Those would be inappropriate. There's this big mismatch between their test statistic and the summary statistic that we're reporting. The general recommendation is use the randomization test. You can always just plug in the statistics you want and have it match the way you're reporting them in your results. That's great. It also has very few assumptions about its usage. It's just this mechanical shuffling. With that in mind, though, the one that's most convenient and easy to use still today is the student's t-test, and that's what I would recommend for homework 3. All right, so where do we actually see that? Let's take a real quick look here. See if I can find it. So here's the, oh, not quite yet. Let's get it over there for you. So here's the Bolt and Gatlin data. What I did here is I got these 2 columns for Bolt and Gatlin, just like you can have 2 columns for your runs, and you can run the t-test over them, and you can see the help for it, and we can see that first we start with one array and then another. How many tails do we have, and what's its type? And your type is 1. All right, you can always click on these to get the actual help message. So paired test is type 1, and thus this is why this function works for us. All right. So yeah, you don't have to have a piece of code that computes your statistical significance. You can absolutely pull the scores that you produce for these measures for your runs and put them into Excel and go across and test the statistical significance with that in Excel. All right. So that basically concludes us talking about statistical significance tests.